Greetings to you. Welcome to Physics with Ben. Don't forget to subscribe and share this video to those that need it. In today's video, I want to teach you guys how to run alternative to particles. A good number of you have asked me to produce a video on alternative. It is a video to help you guys prepare ruggedly for your forthcoming GCE examinations. The book before me here is a very good book for this exercise, written by Dr. Chris U. Ugenie and the IEC team. You can check this book in any bookshop close to you or click in the description box below to get the contact of the authors so that you can place your order. So, let's get straight to the business of the day. We want to run an alternative to particles. So for the stuff you need for this experiment, you need this book, or you may look for any book that is alternative in nature, and then follow what I have done in this video, and then you just get your results. You need a calculator, you need a WAEC standard graph. Yes, this is what I'm using for this video. And then your 30 cm transparent ruler, then it's a pencil, and then we are good to go. So let's get straight to the business of the day. This is what you will see on the day of your GCE or IGCSE alternative to particles, whatever. It's how to look like. So how do you go about it? You have to mentally run the experiment as though you are in the physics lab doing it practically. It's very simple. This is the diagram provided. So let's read together. A circuit is connected as shown in the diagram above. With the key closed, the rheostat is adjusted such that a small current passes in the circuit. The current I in the circuit is measured and recorded. Also, the potential difference V across the 2 ohm resistor is measured and recorded. The procedure is repeated 4 more times by adjusting the rheostat each time to obtain higher values of the current and the potential difference. Figure 3a shows the values of the current I subscript I, while figure 3b shows the corresponding values of the potential difference V subscript I, where I is equal to 1, 2, 3, 4, and 5 respectively. These are the diagrams. Figure 3a, figure 3b. Now these are the instructions. Read and record the values of the current I. Evaluate I inverse in each case. Also, read and record the corresponding values of the potential difference V. Evaluate V inverse in each case. Tabulate your readings. Plot a graph of V inverse on the vertical axis against I inverse on the horizontal axis, starting both axes from the origin 0, 0. Determine the slope S of the graph. Evaluate K is equal to S inverse. State 2 precautions you would take to ensure accurate result if you were performing this experiment in the laboratory. You may screenshot the remaining information and then we'll use it later. Thank you. So let's go straight to the point. First things first, pick up your graph book and do as I do. Do as I do. It is a graph of V inverse versus I inverse. So just as I told you in the other videos I produce on re-experiment in the laboratory, both in the major experiment and alternatives to practicals, especially in GCE and in WAEC, the table of values carries the highest mark. You can afford to toy with this. So I will teach you how to generate table of values even here. Beginning from this number, I down are the instructions that you need to pick up. Now here is I. This I simply means the number of time. This I simply means the number of time the experiment is to be performed. You have I subscript I here, meaning I1, I2, I3, I4, I5. V1, V2, V3, V4, V5. That's the meaning of VI and II. Good. So the first thing we are going to do on our table of values is to write observations or table of values. Good. So we may choose to write serial number or I. So, but for the sake of this exam, let's choose I in place of serial number. So, write I and draw a line. Mind you, your I is up to 5, meaning we have to perform, the experiment was to be performed 5 times in the lab. 1, 2, 3, 4, 5. Good. So we write 1, 2, 3, 4, and 5. That's it. The next thing we are to do here, they ask us to read and record the values of I. You can see that. So this I is a composite parameter. So we place it here. I/ampere. We draw a line. Good. The next parameter is evaluate I inverse in each case. The next parameter is I inverse. I inverse, so slash A inverse. You draw a straight line down. The next parameter is V, the potential difference, the voltage V. So you record V/volts. You draw a straight line down. The next parameter is evaluate V inverse in each case. You record V inverse/volt inverse. And that is the last parameter. The next thing is to input the values. But before we do that, take notes. This is the composite table. The composite table. So let's rule this here neatly. Don't forget I told you that your table of values carries the highest mark and you need not toy with this. So we are set to go. Now, we are to read this. This is your supposed ammeter, and this is your supposed voltmeter, as you see in the other videos I have produced. Now, before we do that, let's look at the calibration of this ammeter and voltmeter. Mind you, I told you the voltage is an independent variable, while the current is a dependent variable. So this guy depends on the value of this guy to increase. Good. From the equation, V is equals to IR. That is it. So we record V, this is I1 with V1, I2 with V2, I3, and so on and so forth. So from here to here is 0.5. We have small calibrations. 1, 2, 3, 4. 0.5 divided by 1, 2, 3, 4, 5 will give you 0.1. It means that each of this calibration is 0.1. Down here, you also have 0.5. 1, 2, 3, 4, 5. Each calibration down here is 0.1. That is what you must keep in your mind. So let's start reading. When the voltage V1 was what? 0.1, 0.2. V1 is what? 0.20. We record everything here to 2 decimal places. I1 was what? 0.1. So this is your I1. You record 0.10. 0.1. Look at it here. 0.1. When V2 was what? This is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Yes. When V2 was 0.60, I2 was what? 0.1, 0.2, 0.3. 0.30. When V3 was what? 0.5, 1, right? 1.1, 0.2, 0.3, 0.4 was 1.4. V3 1.4. 1.40. I3 was what? I3 was 0.5, 0.6, 0.7. 0. What? 7. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 was 0.7. When V4 was what? This is, let's count. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17.5 is in the middle. So 17.5. So we say that 17.5 times 0.1. That will give us 1.75. So when V4 was 1.75, V4 was 1.75, I4 was what? I4 was, this is 0.1, 0.5, 0.6, 0.7, 0.8, 0.9. I4 was 0.9. Sorry, this is 7090. Good. The last calibration, when V5 was 2.4, this is 2. 2.1, 0.2, 0.3, 0.4 was 2.40. I5 was what? This is 1, 1.1, 1.2. 1, 1.1, 1.2. So record 1.20. So we are done transferring these values on the table of values. So the next thing to do is to find the inverse of I and the inverse of V. It is simply saying 1 divide by this, you put the result here. 1 divided by this, you put the result here. Quick, let's go. So we'll have 1 divide by 0.1. We have 10. We record this and this to 3 decimal places. So we have 10.000. Good. We have 1 divided by 0.3. What do we have? We have 3.333. So we are done with this column. The next one is 1 divided by everything here. So we'll have 1 divided by 0.2. We have 5. We'll record it as 5.000. So we'll have 1 divided by 0.6. We have 1.667. So we are done generating the table of values, the most important section of this alternative to practicals. You may screenshot this. Good. Now let's just look at the table and predict how our graph will look like. Don't forget from the equation V is equals to IR from Ohm's law. V and I, when R is constant, they are proportional to each other. They are directly proportional to each other. Meaning increase in V will cause an increase in I, and decrease in V will cause a decrease in I. So if V and I are involved in an experiment, you're going to have the trend of an increase or decrease trend. Meaning your graph, when plotted, will look like this, or will look like this. Any of this graph, one graph passing through the origin, the first one with an intercept is y is equals to mx plus c, and this one y is equals to mx, and then this one y is equals to what? Mx plus negative what? C. So you may have graph 1 or graph 2 or graph 3. These are the possible graphs we are going to have in this experiment. So let's look at the trend to confirm what I said if it's correct. So when the values of V were increasing down from 0.2 to 0.4, the values of I also increased from 0.1 to 0 to 1.2. So you have an increase trend. Any of this graph will be part of that. And then the inverse, when the value of V inverse decreased from 5.0 down to 0.4, the value of I also decreased from 10 down to 0.8. So you have a decrease trend. So whichever we are asked to plot, in this case, a graph of V inverse against I inverse. So we're going to plot a graph of decrease. So any of graph 1, 2, 3 will be the graph we are going to get at the end of the day. So the next line of action is for us to plot the graph. But before we do that, let us find the suitable scale for this graph. This is Y and this is X. Good. So the guys, this is tabulate your reading. This is V of the question. We are done with this. Very, very okay. Then we are on VI, plot your graph. We are on VI, plot your graph. So they ask us to plot a graph of V inverse on the vertical axis and I inverse on the horizontal axis. So the highest value here is 5, and the highest value here is 10. We can say that for the vertical axis, let 2 cm be equal to what? 1 unit. 2 cm to 1 unit. And this wire graph is designed in 2 cm. This wire graph is designed in 2 cm, meaning in 2 cm you have 10 small boxes. Let's count. This is 1, 2, 3, 4, 5, 6, 7, 8. So, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 2 cm gives you 10 small boxes. So each 2 cm you add 1 unit. Good. So let's do that quickly. 2 cm to 1 unit. So on the y-axis, this is let's call it, change it, V inverse axis and then I inverse axis. Here we said let 2 cm be equal to what? 1 unit. How about here? The I axis. Can we say 2 cm to 2 units. Good. So this is 2, 4, 6, 8, 10. Yeah, that will go. Okay, let me say 2, 4, 6, 8. Okay, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Okay, we can say let 4 units. Let 4 cm 2, 4, 6, 8, 10. We can say let 4 cm be equal to what? 2 units. That's it. So we can say let 4 cm be equal to what? 2 units on the I inverse axis. So we are done defining our graph, straight to the point. So we agreed to start our graph at the edge here. So we're going to draw a straight line here. Let's draw a straight line here. And the examiners asked us to start our graph at the origin, 0, 0. Good. Then you put an arrow here to indicate the direction of the graph. And don't forget, this is V inverse slash volt inverse. And we said here, let 2 cm be equal to 1 unit. So let's start our graph. This is 1, 2, 3, 4, 5. We can shift our graph up here. We can shift our graph up to this place. 2 cm to 1 unit. Let's see. This is 1, 2. This is 1, 2, 3, 4, 5. Good. We can even shift it up here again. This is 1, 2, 3, 4, 5. Good. So at this point, we can draw another straight line here. Good. And then this is 0, 0. And then this is 1, 2, 3, 4, 5. So the highest vertical value here is included in the graph. The next thing to do is to include these values now. So we agree that 4 cm to 2 units. So this is 4, it's another 4, another 4, another 4, and then another 4. Put an arrow here. This is your I inverse slash A inverse. Good. So this is 2, 4, 6, 8, and then 10. 10 is here. Good. The highest value is represented. The next thing to do is to find the value for each small box. The value for each small box is very, very important. Here, the value for each small box is gotten by saying 1 divided by 10. So we say 1 divided by 10, 0.1. So the value for each small box here is 0.1. That value is very, very important. The value for each small box here, we say 2 divided by 20. 2 divided by 20, still 0.1. So here too, the value for each small box here is what? 0.1. Good. So, how are we going to make use of these small values? Every item on this table divide by 0.1. Every item here divide by 0.1 will give us the exact value that we need to represent on the graph. Every item here divided by 0.1, every item here divided by 0.1 will give us the exact values that we need to represent here. Probably to 2 dp precisely, or to 1 dp. So let's go straight to the point. Let's start plotting the graph now. Let's start plotting our graph. So when V inverse was 5, right? What was the value for I inverse? I inverse was 10. Good. When V was 5, I was 10. So this is 5. You put your ruler and trace, this is where 5 is, and trace 10. Where they intersect, you put a star there. That value is plotted. Good. When V inverse was 1.667, how do we get this value here? Very simple. Just divide the whole of this by 0.1. So we say 1.667 divided by 0.1. We got 16.67. Approximate that to the nearest whole number, that is 17. It means we are going to count 17 small boxes to get this value. Let's do it. So this is 10. This is 10, 11, 12, 13, 14, 15, 16, 17. This is where 17 is. If you don't want to confirm, just say 0.1 times 17. You will get 1.7. So indirectly, we are working with 1 dp here. That is 1.7 approximately. Good. So that is what we are going to do for all the values. So 1.7 is located here. 1.7 against 3.333. How to get that value? Just say 3.333 divided by 0.1. What do you have? You have 33. 33.33. To the nearest whole number, 33. So it means you have to count 33 small boxes to get this particular I inverse value. So let's count. This is 10, 20, 10, 20, 30, 1, 2, 3. This is where 33 is. So you trace this line. You trace this where the line meets with this. That is the value. Good. This is the point. That is the point. So we're going to replicate what I just did here for all the values. Good. And so we are done plotting all the values now. So these are the points. So we have 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5. All the points plotted correctly. The next line of action is to draw our line of best fit. So this is why I always insist on the use of this ruler. You put your ruler here, you put it here. This graph is a perfect graph. We have this value, we have this, we have this. Good. You now draw a straight line. Don't force your line to pass through the origin. It will naturally pass through the origin. What do you see? Perfect. I predicted 3 graphs. And right now, this graph is a graph we have. The graph is passing through the origin with no intercepts. No intercepts. So let's find the slope of the graph. Let's find the slope of the graph. To find the slope of the graph, we are going to choose a very big triangle. So let's choose this point. Let's choose this point. Take note. This point, and then this point. Your triangle must be big in that it reduces the error in the experiment. Good. Don't forget to subscribe to this channel and share this video to those that need it. Promote this channel and God will bless you. Good. We are done drawing our triangle. So you trace this line, dot, 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 dot. And this is your I inverse 2. You trace this line, dot, 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 dot. And this is your I inverse 1. You trace this line, dot, 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 with broken line, dot, 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 dot. And this is your V inverse 2. And then you trace this one, dot, 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 dot. And this is your V inverse 1. Something as neat as this. Good. So the slope of the graph is simply given as change in V inverse divided by change in I inverse. So these values are so neat. Your V2 is exactly on 4. So you have 4. So this means, V inverse 2 minus V inverse 1 divided by I inverse 2 minus I inverse 1. So if you evaluate correctly, you have V inverse 2 is 4. 4 minus 1 divide by 8 minus 2. So you have 3 divided by 6. 3 here 1, 3 here 2. What you have is 0.5. Yes, I'm correct. So therefore, there's it. 3 here 1. This is, so your slope is 0.5. So dimensionally, what you have here, you have V inverse all over A inverse. So your slope is simply 0.5 arms V inverse. This is the value for your slope and the SI units. So the next thing they ask us to do, they ask us to evaluate K is equal to V inverse. Sorry, S inverse. So we have K is equal to S inverse. That is question number VIII. Evaluate. We are done with V, the slope. The slope is VII. Yeah, we are done with that. So question number this, evaluate K, S is equal to S inverse. So this simply means 1 divided by the value of the slope, and that will give us, that is 1 divided by 0.5, that will give us 2. So that will give us 2. This time V inverse will change to V, and then you have A inverse. So the value for K is this. Good. The next thing they ask us to do, they ask us to state 2 precautions. That is X. Now there's a way you state precautions when it comes to alternative particles. You don't say I avoided error due to parallax when taking reading on the ammeter. I avoided error due to, no, you don't do that. You say I would have avoided error due to parallax when taking reading on the ammeter. That's number 1. I would have ensured tight connection. And so they say 2. This is how to state them. I would have avoided error due to parallax when taking reading on the ammeter and the voltmeter. Number 1. 2. I would have ensured tight connection. Good. The next thing they ask us to do here is BI and BII. They ask us to calculate. I will just collect the data for us quickly and then solve the question. I don't like my videos to be long like this, but this video can stop any moment from now, but let's see how we go about it. Quick, this is what we have. In case the video stops here, you can go ahead and solve this question, but I'm done with the basics of alternative particles. So this is BI. A cross-sectional, a wire has a cross-sectional area. Our A is given to be 4 times 10 to the power minus 8 to the power minus 8 meters square. The resistivity rho is equal to 1.1 times 10 to the negative 6 ohm meter. And then if the resistance of the wire R is given to be 11 ohm, it's made of the wire. Calculate the length of the wire L is not given. Now remember that the resistance of a wire is directly proportional to the length of the wire and inversely proportional to the area, if I'm correct. Yes, inversely proportional to the area, so that your R is equals to rho L all over A. Yeah, this is the equation. This is the equation, I suppose. Let me verify. Okay, I'm correct. So the next thing to do, they're asking us to find the length of the wire. So this implies that the rho L is equals to RA, and this implies that rho L is equals to RA divided by the resistivity. So this implies that the length of the wire is equals to R times the area divided by the resistivity. So this is the same thing as 11 ohm times 4 times 10 to the power negative 8, 11 ohm times 10 to the power negative 8 meter square divided by 1.1 times 10 raised to negative 6 ohm meter. So ohm will cancel ohm, and meter will cancel 1 meter here, left with 1 meter here. So this is the same thing as we have 11 times 4 times 10 raised to the negative 8. 11 times 4 times 10 raised to negative 8. That will give us 4.4 times 10 raised to negative 7 meters divided by 1.1 times 10 raised to negative 6. Do that correctly, you have that answer divided by 1.1 exponential negative 6. And the length of the wire is 0.4 meters. Therefore, L is 0.4 meters. That's it. The last but not the least, the examiners ask us, we are done with this, that is BI. This is question BI. The next one is BII. A cell supplies a current of I. Let's collect our data quickly. A cell supplies a current of I, we have two currents here, so we have our I1 is equals to 0.6 amps. Our I2 is equals to 0.2 amps. And then through a resistor, our external resistor R1 is equals to 1.0 ohm. Our external resistor R2 is equals to 4.0 ohm. And then they ask us to find the internal resistance of the cell, meaning R, this the cell is the same, so to have the same internal, the cell is the same, so it will have the same internal resistance R. So they ask us to find the internal resistance of the cell. So how do we go about it? Recall from E is equals to I into capital V plus small v. Capital R plus small r. Capital R plus small r, which is the same thing as big V plus small v. where the big V is known as the terminal potential difference, while the small v is known as the loss voltage. So we call this is E1. E1, we call it equation number 1. So we have, let's call this our I2, and then our R1, our R1. So we have our I2, E2 is equal to I2 into R2 plus R, which is the same thing as V, capital V plus small v, equation number 2. So we're going to equate this to this. If we do that correctly, we are going to have I1 into R1 plus R is equals to I2 into R2 plus R. We now substitute the values. Our I1 will have 0.6 into 1.0 plus R is equals to I2 is what? 0.2 into 4 plus this. So you expand the bracket and you collect the like terms. Good. So we have 0.6 times 1 will give you 0.6. 0.6 times 1 gives 0.6. So 0.6 plus 0.6 R 0.6 R is equals to 0.2 times 4 gives 0.8, I suppose. Yeah, 0.8. 0.2 times 4 gives 0.8. I was correct. We have 0.8 plus 0.2 R. You collect like terms. So we have, this is 0.6. So we have 0.6 minus 0.8 is equals to 0.2 R minus 0.6 R. So we have, this is 6. We have minus 0.2 is equals to minus 0.4 R. This cancel this. This cancel this. Then we have 0.2 is equals to 0.4 R. Divide both sides by 0.4. This go. So therefore your R internal resistance is 0.2 divided by 0.4. So we have 0.2 divided by 0.4. We have 0.5 ohm, and that is the final answer. To this, we have come to the end of this video. I'm sorry, this video is the longest video on this channel. Bear with me, I didn't make them separately. I make the whole thing, the whole package, everything is insane. So don't forget to subscribe and share this video to those that need it. This is the B part, BI of it, the BII, and this is the concluding parts. And this is the question, the diagram, table of values, and then this is the graph. To this, we have come to the end of this video. Bye bye. God bless you.